Hi, and welcome to an introduction to calculus. This is a topic that a lot of students find really hard. I know my own students, they often call it calculus, get it? But yeah, it can be really tough. I think the reason it's tough is we have some weird symbols being introduced. And I think another tough thing is that it ties everything together, which actually is a good thing. And it means you have to understand functions and graphs, so we'll talk about gradients and areas and parallel lines and perpendicular lines. It puts everything together. I don't know if you've ever seen this really old reference right here. This is from a movie called The Big Lebowski about a rug that tied everything together. But in any case, in calculus, our main goal is to do two things. We're going to be mainly focused on something called derivatives and something called integrals. That's going to be our main goal. And in this video, I don't necessarily want to go into all the details. The point here is just to motivate you to kind of give an overall idea of what we're going to be doing. Because the concepts themselves, I think, are quite straightforward. I think they're quite understandable. So let's see what you think. I'm just going to try to give you an intro to, first of all, something called derivatives. It's something you already know about. Because a derivative is just a rate of change. That's all a derivative is. It's how something changes with something else. So like, we have lots of ideas about those things. We're gonna talk about, delta y over delta x. Do you remember seeing those kind of things? That's actually a rate of change. It's how something changes with something else. So we've learned this, haven't we? Haven't we learned this in other topics, that we know how to find a gradient of something? And that's my whole point, is that I think maybe you already know how to do that. If I give you some sort of straight line, like let's say it's f of x equals 2x plus 3. Do you know what that would look like? I don't know if you remember this as a straight line, ax plus b or mx plus b, where this is the gradient, this is the y-intercept. So I could guess that the y-intercept, let's see, it looks like it's at plus 3, so maybe it's up here, maybe this is 3. And then this line might go, let's see, for every 1 unit I go to the right, I have to go up 2, so I don't know, I'm just going to guess. Keep in mind, I don't have scale on this, but something like this. This is at least what this graph might look like, depending on how I put the scale. All right, well, how would I find the gradient of this? I think you already know how to do that, don't you? Or maybe you do, I don't know. But the gradient, so we'll say this, the gradient, maybe you remember doing this from other topics, right? We often call it m for short, or we can call it delta y over delta x, which is like a change in y over a change in x, which is a rate of change. Which could be seen as, we can write it as like y2 minus y1 over x2 minus x1. All that stuff is actually finding a derivative. So if I say, hey, I want you to find the derivative of this thing, all it means is find the gradient of that line. Piece of cake, right? What's the big deal? Well, if it was just this, calculus wouldn't be hard. So the whole question is, if the gradient is constant, the derivative is constant. In other words, here, this gradient, it's not changing. Look at the slopiness of this. If I look at how steep this hill is, isn't it the same steepness everywhere? Well, that makes it easy. The gradient, then, is the same everywhere, which means the derivative is the same everywhere. But what happens if it's not a straight line? See, what happens if it's not a straight line? So maybe, I don't know, I'll just try something that's not a straight line. Maybe something goes like something like this. Uh-oh, now what? Well, we have to take a look at what this means and what to do here. And most people have some idea. What we do is we're going to say, all right, it's the gradient of what we call a tangent line. In other words, we're going to be caring more about where we want the derivative. That's going to be the key word here, is where are you looking? Because this thing has a different slopiness everywhere. Look, right here. Actually, I want to explain this maybe. I consider derivatives just like if you're walking up or down a hill. So if you imagine you're walking to the right. I always imagine I'm walking to the right because as x's get bigger. If I'm walking to the right, can you see that I'm going down a little bit of a hill here? Oh, now I'm at the bottom. Now I'm going up a hill and it's steeper. If you just think of it as that, you'll have a really good idea what to do. So if I want to draw a tangent line, I'm really asking, how steep is this hill right where I'm standing? Do you see it depends where I'm standing? If I'm standing here, I'm really going up a hill. It's very steep. Here, it's really flat. Here, it's also flat. Here, I'm going down a hill, but it's not so steep. So really what matters then is we have to pick some point. Let's say I pick this point right here. What I imagine I do is, can you imagine zooming way in on this one point right here? Can you imagine if I did that? Can you see that this would be like this, and there we would have what we call a tangent line. So it's a line that shows what the graph is doing at that point. I'm trying to draw it something like this. It's going to be some sort of straight line like this. That's because as I zoom way in, if I zoomed in on this one point, you see it would look like the line is going something like this. It looks like it's a pretty straight line, isn't it? Just at that point. It's different everywhere. And that's the whole idea, is we draw things called tangent lines, and we just look at what the derivative is or what the gradient is. So if I say I'm going up a hill, then I could say the derivative is positive, because the gradient is some positive number. So in other words, right here, I'm going to say this. I'm going to maybe write it down here. I'll say derivative here. Derivative, I'll just do deriv for short like that, okay? Derivative equals positive, because I'm going up a hill. All right, well, what is it right here? What is it right there? Well, if you had to guess, how steep is this hill right there? Can you see it's not steep at all? In fact, it's flat. I'm going to just try to move this just so I get it like this. So right here at this point right here, this tangent line at this point is actually flat. Well, if it's flat, that means the derivative, let's see, the gradient would be how much do I go up for how much I go over. That's how we define it, right? We define it by a gradient here. But if I'm not going up at all, well, then my derivative equals 0. So that's hopefully making sense. How about right here, let's just say, right at this point? What's going on there? I just want you to think, about these derivatives just as steepness of lines. Can you see? Well, I didn't really draw it very well. Something like, maybe something, I'm just trying to make it match the graph. Something like that, maybe. Can you see? Maybe something like that at this point. All right, so what would the derivative be there? Can you see I'm going kind of down a hill? So I'm going to say the derivative here, derivative equals negative. Do you see that? And right here, guess what? The derivative here is going to be 0 because it's also flat. So do you see, it all depends on where we're looking. So the really important thing with derivatives is, where are we actually looking? Because the derivative is different everywhere, on this graph at least. So here, for example, at this point here, I could say, right here, I could say the derivative equals 0. By the way, if you understand this idea, this is it. This is how derivatives work. There's nothing more to it. Down a hill, by the way, derivative is negative. So this is really a nice overall trick. This is what I use to help me understand what everything is. I use this to help students as well. So if this makes any sense to you, congratulations. You understand derivatives. You just got to draw yourself a tangent line of that graph at that point, and you just find the gradient of that tangent line. And sometimes it's harder. I'm going to show you some really cool tricks on how to actually do it, but just so you know, that's the idea behind it. Now, what's an integral? Remember I promised you there was 2 different parts to it. Remember I said there's derivatives and integrals? We've covered derivatives now, gradient of a tangent line. You can also say it's a rate of change. We're going to learn some things about the notation. But the second part is something called integrals. And an integral is just the area under a curve. That's it. So for example, this curve right here, f of x equals 2, it's a straight line. Well, a curve can be straight. And I want the area between x equals 0 and x equals 3. So let me just try to do that here. So I'm going to take a look at this. I'm going to draw myself, well, from x equals 0, which is right here, to x equals 3. We go like this. And I have to find this shaded area here. Well, how would I find that? I know that the area of a square, at least, or a box, is just the length times the width. So it would be 3, because it's 3 long here, times 2. So the answer would just be 6. That's it. Do you notice how easy that was? The area is 6, whatever units these were. So units squared, whatever those are. Maybe they're meters, then it'd be meters squared or whatever. That's it for areas. So what's the big deal? Well, again, if it's a straight line, it's easy. But if it's a curved thing, then it's harder. So that's why I said that wasn't so bad. But I mean, what if the graph isn't a straight line? What if it's curvy or nonlinear? We're going to learn some tricks for this. Just so you know, it depends on which class you're in, but there's one thing. You could approximate this with a whole bunch of rectangles. You could actually say, all right, I'm going to just draw a whole bunch of rectangles and just find the area of those. Can you imagine doing something like this? That's actually one trick for calculus. It depends if you go on the left side or the right side, if you understand what I mean here. Like, are you going from the graph to the left, or are you going from the graph to the right? So on. So, I mean, you could be doing things like this. That's one way. So you could approximate like this with a bunch of rectangles. There is an even more accurate way to do it, which is you could use what we call trapezoids. So let's say we have something that, I don't know, maybe goes like this again. This time you could represent it, instead of doing, do you notice you're going to be underestimating the area? You could instead draw yourself a bunch of, watch these, you can draw yourself some trapezoids like this right here. See, these are even better. Do you notice? And I'm sort of matching what the graph does like this right here. And I'll just find the area of each of those trapezoids. Hopefully I keep the distances the same here. Something like this. Okay, so you could actually approximate using trapezoids. That's what those are called, these little shapes here. That's one way to do it, but I'm going to show you an even better way, because did you notice you can approximate this? You're going to be better if you have more rectangles or more trapezoids. Does that make sense? Like, the more of them I have, the better I'm going to be, because I'm still going to be missing parts of the curve, depending on how curvy it is. So an interesting thing is, what if you have an infinite number of infinitely small rectangles? Well, then you get to the answer. And I'm going to show you, we're going to just wave our hands, have a magic trick, so we won't even need to use this to approximate. If we have the equation at least, so if we're given the equation, finding the area under the curve, the exact value, will be super easy. So I'll show you like a magic trick, so maybe then you don't feel like this little raccoon here. Finally, I'll give you a question that basically, it has all the ideas and concepts you need for calculus, at least for derivatives and integrals. So let's just take a look at this particular graph here. We don't know the equation for it, but I want to know, what's the derivative at x equals 2? Remember what a derivative is. It's just a gradient of a tangent line, in this case right here. So it's just a gradient. I want the derivative here. It's also just a gradient. Okay? So that's not so complicated. What's the integral? That's just the area under the curve. You just got to remember those definitions. So let's take a look at this, see if we can do it. If I want the gradient at x equals 2, well, at x equals 2, what's going on? At x equals 2, do you notice we're at this point right here, whatever that is? I don't care about the actual point. I care about the slopiness of it. Do you see we're on this part of the graph here? I just need to know, what's the gradient of this line? Well, to do that, I can just find any 2 points. I'm going to use good old-fashioned rise over run. I'm going to use this right here maybe as my second point. This is my first point. You know what I mean? I can go like this right here and say, all right, this will be my delta y. This right here will be my delta x. So my gradient then will just be, actually I shouldn't say gradient, I'll say derivative, because that is what it is, which is the gradient. Remember, they're the same. So the derivative is equal to, let's see, it's going to be delta y, which goes from 0 up to 3. So it's going to be delta y over delta x, which is equal to 3 units up over 3 units across. 3 over 3 is just 1. So my gradient is 1. In other words, my derivative is 1. Does that tell you something? It means you're going up a hill. It's positive. How about the gradient at x equals 6? Let's do that one. So this one right here, maybe I'll do it in a different color, do it in green maybe. So at x equals 6, let's look at that. That's this point right here. At this point, do you notice the gradient is flat? It's flat. So what does that mean? Well, the derivative, remember, which is equal to delta y over delta x, I could pick 2 random points, but how much it goes up or down is 0. Do you notice the delta y is 0? It's 0 over anything. So I could say 0 over, I don't know, let's just say we use all the way over to 8. So let's say you go from 3 to 8. So let's say 0 over 5, for example, still equals 0. So do you see that's why my answer is still 0? So what does that tell me? Well, that tells me that, well, my derivative is 0. That's okay, because it's flat. That should make sense. Let's find the area under the curve. That's what the integral is. The area under the curve from 0 to 8. This becomes a bit harder. So let me try to just estimate this. I'll just draw like this. And I'll draw my little graph again. I'll just try to estimate. I'll just go like this and like this. I'm just doing it freehand. Whoops, that was very bad. Something like this. And this here is my x's and here's my y's. Well, I got to find out the area under this whole thing from 0 all the way to 8. If I want to do that, maybe it helps to split it up into 2 shapes. Can you see there's like 2 nice shapes I could draw? I could draw this one. I can call it maybe 1, and I'll do this one. Maybe I'll call it 2. Well, the area, let's see, what it'll be. It'll be area 1, so maybe I'll just call it A1 plus A2. Now, this is a triangle. Do you know how to find the area of a triangle? The area of a triangle is base times height divided by 2. So I'll say that. So 1/2 base times height. And area 2 will be, well, this length times width, if you want to call it length and width or something like that, or length times height. I don't know. We can call it base. We can call this height. We can call this here the length right here. We can call this here the width. I don't know. Just to use things you've probably heard of before. Let's actually go ahead and figure this out. So the area then will be, let's see, it's 1/2 times this base right here. How far is this? This is 3. And how tall is it? Well, it's also 3 tall. I add to that the area of this rectangle. Now, this is not 8 long. It only goes from 3 till 8. Do you notice that? This right here, remember, this number right here is 3. This here is 8. From 3 till 8 is actually 5 units across. How much do you have to go up? You still go up 3. All right, so let's see. This is 3 times 3, which is 9. So it's 9/2 plus 5 times 3, which is 15. Okay, now what? Well, I mean, we could just get it as a fraction. I mean, we can just get a common denominator. I need them both over 2. So I got 9/2 plus I need something over 2. What do I do here? Well, this is like a 1. 1 times 2 is 2. So 15 times 2 is 30. That's the same. All right, so then I could say it's equal to 39/2. That could be my exact answer, right, if I want to do it exactly. Of course, you can do it on a calculator, but my point was just to show you that you can get this answer depending on what you need to do here. Okay? I hope this helps you to understand a little bit about calculus. The whole point is to try to look at this right here and just look at these two ideas. Derivatives, what are they? That's just the gradient. I'll just write that down. Here's the gradient of a tangent line. This is really the whole thing, right? Gradient of a tangent line. And what's the integral? It's just the area under a curve. The rest is just details. So I'm going to be showing you in other videos, of course, how to do it, how do we practically do it when we have complicated looking equations. But the ideas are really, they're just this simple. Gradients or areas. Boom.